Property-based testing is a principled way of testing software that focuses on functional specifications rather than on suites of input-output examples. It has been popularized by libraries like QuickCheck in Haskell. If we want to test a function f, we can define a property p that defines some correctness condition. We'd like to know that for all inputs x, p holds. One way to go about this is to generate random inputs and check p for those inputs. If one of the generated inputs is a counterexample for p, we know that there's a bug in f. As we test more and more inputs without finding a bug, we gain confidence that f is correct. Property-based testing is great, but it's not perfect. It can take a lot of inputs to find a bug. Some of those inputs will be interesting, but many will be similar to each other, which wastes time and testing effort. In our paper, Do Judge a Test by its cover, we use insights from combinatorial testing to make this process more efficient and find bugs using fewer tests. In this talk, I'll start off with an overview of combinatorial testing. Combinatorial testing is based on a metric called combinatorial coverage, which measures the proportion of the overall input space that a given test suite represents. This metric will be our starting point for optimizing the property-based testing process. Before we can apply combinatorial coverage to property-based testing, we'll need to generalize a bit. Part 2 of this talk discusses our extension of combinatorial coverage to work with algebraic data types. Our generalized notion of coverage is based on regular tree expressions. I'll explain how this formulation makes our definition of combinatorial coverage expressive and flexible. Finally, in Part 3, I'll talk about our implementation, which we call quick cover. Our algorithm uses combinatorial coverage in a non-standard way. While classical combinatorial testing tries to maximize coverage, in other words, get 100% of the possible coverage, quick cover goes a different route. It uses combinatorial coverage to thin an existing property-based testing generator and guide it to more interesting tests. I'll show that this approach actually works. In one of our case studies, quick cover finds bugs using an average of 10 times fewer inputs than QuickCheck. Classical combinatorial testing is employed to test software systems with a set number of configuration parameters. As a running example, consider a web application that can be configured to optimize for different choices of browser, use different databases, change depending on the user's admin status, and run in different languages. For our purposes, assume each of these parameters can only take 2 different values. Obviously, testing the system in a single configuration is not good enough, but testing in every configuration might be impractical. Luckily, we might not actually have to test everything. It's fairly rare that every single configuration parameter affects the behavior of a particular part of the program. Instead of caring about the configuration of every parameter at once, it might suffice to pay attention to just t of them at a time. For example, we should make sure to test our application when optimized for Chrome and set to admin. But while doing that, we can test whatever settings of the other variables we'd like to. If we choose MySQL for the database and English for the language, we not only test that two-way combination, but also the combination of MySQL and admin, English with Chrome, etc. By focusing on two-way combinations instead of the full four-way ones, we can see that any given configuration actually tests a lot of different behaviors. We might ask, how many inputs do we need to test all two-way interactions between parameters? The answer is actually just 5. Even though there are 16 possible tests, this set of 5 covers all two-way combinations of parameter values. We say that this test suite has complete two-way combinatorial coverage. Testing in this way becomes even more efficient as the number of parameters grows, since the number of interactions each test covers is exponential in the total number of parameters. All of this is interesting because there's real data to suggest that maximizing t-way coverage for small values of t can greatly increase bug-finding potential in the real world. In a NASA study of a system with 100 known failures, 93 were caused by one or two-way parameter interactions, and the remaining 7 were caused by no more than 4 total parameters interacting together. In other words, 100% four-way combinatorial coverage is sufficient to find all bugs in that system. Now that we know combinatorial coverage is a useful metric for finding interesting tests, we can consider using combinatorial coverage to aid property-based testing.
But wait! Combinatorial coverage is only defined for simple parameter tuples. How are we supposed to use it with QuickCheck when we have much more complex algebraic data types?
Good point, John. Let's explore that next. We're going to generalize combinatorial coverage by leveraging regular tree expressions. These are similar to the string regular expressions that you're used to, but they encode sets of trees instead. This expression encodes lists of booleans. The plus operator denotes a disjunction, the mu operator is used for recursion, and anything else is a constructor. In this example, there's one case for nil and another for cons, just like you'd define in a language like Haskell. In fact, regular tree expressions subsume basic algebraic data type definitions. Of course, regular tree expressions can also express more granular sets of trees. Let's look at a couple examples. This expression denotes all single-element Boolean lists. This one describes the set of lists containing only true. And this last one describes lists where true appears at some point in the list. Top, in this case, is the regular tree expression that matches anything, and you can think of the outer mu as the part before the first true, and the inner one as the rest of the list. Notice that the configuration tuples we were looking at before are regular tree expressions too, even the incomplete ones that we use to represent T-way interactions. In order to define combinatorial coverage, we need a broader notion of T-way interactions. With simple parameters, it was obvious, but there are actually a lot of options for algebraic data types. We chose to focus on interactions between data constructors. For example, we'll say that this particular list covers the following two-way interactions: true, somewhere to the left of cons; false, to the left of cons; cons, to the right of another cons; false, to the right of cons. Note that this one isn't a direct parent-child relationship, it's transitive. And finally, nil to the right of cons. In order to make this concrete, we need a formal way to name these interactions that captures even transitive relationships, like the one between false and cons. By way of analogy to modal logics, we'll define two operators, next and eventually. Next E is the set of trees with a child described by E, and eventually E is essentially the reflexive transitive closure of next. I'm glossing over some details here, so check out the paper if you want to know more about these definitions. Intuitively, eventually E is the set of trees where some subtree, including the whole tree, is described by E. This captures that somewhere underneath idea that was implicit in the descriptions before. Now we can look at the same list and explicitly write out the two-way constructor interactions that we care about. Note that we don't care where in the tree these interactions happen, so each description also starts with eventually. These regular tree expressions that represent interactions are what we call sparse test descriptions. These are a subset of regular tree expressions which capture exactly the constructor interactions we care about. Before we go on, let's look at a few examples of sparse test descriptions so we can get an intuition for why the interactions they represent are of practical interest. This algebraic data type, representing a subset of arithmetic expressions, has two-way descriptions that look like this. A test suite that covers these descriptions must include inputs with varied nestings of addition and multiplication. This more complicated type, which represents terms in System F, the polymorphic lambda calculus, admits two-way descriptions like these. In this case, we can be sure that a full coverage test suite tests different relationships between lambda abstraction and application. The main takeaway is that the constructor interactions captured by sparse test descriptions are generally interactions that one might intuitively want to test anyway. With sparse descriptions in hand, we can finally give a generalized notion of combinatorial coverage. Combinatorial coverage is the proportion of appropriate sparse test descriptions that describe some test in our suite. This idea specializes to the classical definition of combinatorial coverage for simple configuration tuples.
This looks great, Harry. But now I'm wondering, might there be other ways of defining descriptions that could also make sense?
Yes, Benjamin, there certainly are. Sparse test descriptions capture one way to talk about interactions within an algebraic data type, but you could totally imagine other formulations. One thing that's nice about sparse descriptions and the eventually operator is that they can talk about finite coverage of an infinite type. Even though there are infinite Boolean lists, there are finitely many two-way interactions. This kind of property is important for the definitions to be useful. Speaking of usability, it's time to see how these ideas work in practice. As I mentioned before, the classical approach to combinatorial testing tries to get to 100% coverage. The goal is to generate a test suite that covers all two-way interactions. Our tool, QuickCover, uses coverage a bit differently. We take an existing random generator and thin it. Instead of running every test, we only run the most interesting ones. This kind of approach is particularly beneficial when we want to find bugs using as few tests as possible. We'll talk about a few of those cases soon. Before we do that, let's look at how QuickCover works. The algorithm is fairly straightforward. We start with a generator of random inputs. At each step, we generate some number of inputs, in this case 5, and for each input, we compute how much our overall coverage would improve if we added that test to our suite. We pick the input that increases coverage the most, run the test, and repeat. Compared to standard quick check, we only run 1 out of 5 of the total generated tests. The ones that combinatorial coverage says are the most interesting and different from the ones before. This is really powerful because the tests that we do run are more likely to find bugs. In our case studies, we found that QuickCover runs 10 times fewer tests than QuickCheck to find the same bugs. In situations like continuous integration, where a small, powerful suite of tests is ideal, this is really a home run. Of course, all of this generating and analysis does take some time, and we found that while QuickCover consistently used fewer tests, it wasn't always faster than QuickCheck. Would QuickCover be faster than QuickCheck if the individual tests were expensive to run?
It turns out the answer is yes. We replicated an earlier case study on generating well-typed lambda terms and using them to reveal bugs in GHC's strictness analyzer. We found out that despite its overhead, QuickCover is almost twice as fast as regular QuickCheck. If you want to know more, take a look at the paper for additional details on our case studies and experiments.
Moving forward, we think that generalizing combinatorial testing to work with algebraic data types opens the door for all kinds of collaboration between the two research areas. In addition, QuickCover's unconventional use of combinatorial coverage is clearly powerful and might inform future work in test case generation algorithms. Thank you to the ESOP organizers for publishing our paper and this talk, and thank you for listening.